All right. So hi, everybody. Thanks for tuning in today. So this week, our seminar speaker is Dr. Prakhar Sinha, who just defended their PhD this week, actually, I think 2 days ago at Purdue University. He is a planetary geologist whose research focuses on characterizing the composition and geologic history of planetary surfaces, mainly the planet Mars. And he uses a diverse set of tools, including color images, visible near-infrared spectroscopy, and X-ray fluorescence elemental analysis. And he also does a lot of analog work as well. He has a bachelor's degree in mechanical engineering from Ramaya Institute of Technology in India, and a master's in aeronautics from Purdue University, and soon, as I just said, a PhD in planetary science, also from Purdue. And today he'll be talking to us about the northern layer deposits of Mars. And so now we're switching to talking about ice on Mars. And so thanks again, Dr. Sinha, for taking the time to talk with us. Take it away.
Thank you. Thanks everyone for being here. Thank you, Professor Hernandez, for inviting me for talk. So my research is focused on understanding the polar layer deposits, and primarily through orbital spectroscopy, and also using rover-based analog study to understand cold environments here on Earth. That's my committee. I'm advised primarily by Professor Horgan, and I have Ryan Eving from Texas A&M, who also co-advised, and Mike Sori and Nat Lipton were also on my committee. Okay. Right. Before going, so on the image here, what you see, what you're looking at is peripheral scarp of the North Polar Plateau, and you can see numerous horizontal layers being exposed at the scarp, and at the bottom you can see a giant dune field, and it appears that materials are eroding from these scarp and feeding into the dunes. And so this is a picture of just get a context of what the polar size of the polar deposits are. So these are giant polar ice caps in white, both at the North and the South Pole, and which is quite prominent, other than the two other categories of surfaces which we see on Mars, the light tone dusty surfaces and the dark low albedo relatively dust-free surfaces. And the third kind is the ice-rich, ice-dominated surface on Mars, and that is the focus of my study. So why is this ice so important? Because one, we know that it forms in the poles where temperatures are lower and all the atmospheric moisture just is kind of cold trapped layer by layer every season, annually, every winter season. And what happens is anything that falls on the ice, including gases, gets trapped in these layers. And eventually, year after year, you build up a stack of a geologic record that has a lot of climatic information preserved in it as well. So that is of primary interest here. And in terms of a major planetary climatological studies, this is of significance because on Earth, the climate is driven by a much more complicated process. So if we just want to understand how climate is driven by orbital configuration of a planet, such as its tilt, which is its obliquity, how that drives the climate in a much less complex environment of Mars. So this is the polar deposits are recent. The northern deposits are of a few million year old, and the southern deposits is thought to be about 100 million, 30 to 100 million year old. So very recent in terms of geological timing. On this, we can see how the reason of the buildup of the icy cap. We see that on the plot to the left, we have obliquity versus time. Give me a second, something's. Sorry about that. So, okay, back to the plot. On the left, we have obliquity on y-axis and time on the x-axis. And if you look right at the center, 5 million years ago, there was a drastic change in the obliquity of Mars, with average reducing to around 25 degrees instead of 35. And why that's important in terms of stability of the poles, of ice at the poles, is when you have higher obliquity, your insulation at the pole increases, which means now your the volatiles are more readily sublimated of the surface. And that's also of importance because in terms of water activity, so these changes in orbital configuration of the planet would have definitely changed the extent of water activity that we would be seeing on Mars. So in the present obliquity that we have on Mars, there is more accumulation going on at North Pole. A major reason to study these polar deposits is that it is the only other ice-rich geologic deposit that is known to have preserved climatic history beyond Earth. On the left is a study by Becerra et al. 2016, and what he looks at is the protrusions in the layers that's exposed at the scarp and compares that to the periodicity in the protrusions with the insolation cycle resulting from obliquity changes of Mars. And there's a good correlation between the protrusions and the obliquity cycles. And these protrusions are usually understood to be more resistant portions in the layers, and probably they are much more rich in dust or other lithics. So these ice, if you were to sample these, it would provide similar climate data that you get from terrestrial ice sheets in Greenland or in Antarctica. So you would get composition of gases in Mars's atmosphere over a period of last few million years. You would get information about temperature, atmospheric properties, isotope ratios, and the changes in insolation over the time. So if we understand a simpler climate mechanism of Mars, we could extend that to a more complex world of ours and predict how we would see climate change here on Earth. So in terms of its relevance, it's been highlighted in the decadal survey, falls under priority question 6, and which talks about what influences surface atmosphere interaction and climate evolution on a planetary body. More specifically, the MEPEC goals expresses its interest in reading these records, climate records, which is manifested in terms of ice-rich geological record at the pole. And various reports like mentioned at the bottom, ISEG and MASWG, they recommend a landed mission to sample ice cores to get those climate records. So overall, the Mars polar science has a compelling solar system-wide significance because it would be a great analog to study ice-rich bodies further out in the solar system. If we want to explore and learn more about habitable conditions in the icy worlds, it would be a great first step to explore the ice at the poles of Mars. These ice is also of significance to human exploration because the ice at the poles exchanges volatiles from the northern mid latitudes, which has been significantly looked at in terms of possible landing sites for human settlement. And as you're working to your work towards exploring the cryosphere of Mars, there would be a lot of cryotech development happening. So overall, Mars community recommends in situ exploration of the polar deposits, which has these benefits to have. So one challenge with dating the ice cores would be that we are unsure if there are datable lithics present in the icy layers. The image on the right shows an example of an ice core that has a really nice layer of volcanic ash trapped inside. That's the black ring that you see on the ice. And such layers of ash can be used to get the age of ice. On the left is a picture of a more younger ice core, and you can see the annual development of the stack layer by layer. So you can get the age of this by just counting the layers. But over time, what happens is the layers get diffused, and so to get appropriate, like get the age of the ice, it's we require layers of ash deposits or any other material in the ice that can be age dated through quantitative age dating methods. But with the ice caps on Mars, we're unsure if such datable materials are present on it, because in general, it is understood to contain just airfall Martian dust everywhere, which we are unsure of if it's datable or not. So here is a high-rise image of looking at the scarp of the North Polar deposits, and we can clearly see dark sediments eroding off the cap and moving towards the floor. And that tells us that there are other lithic material than just airfall Martian dust present in these in the polar ice-rich plateau. And that drives the question for my research, which is what non-ice sediments are present in these polar layered deposits, and how did these sediments get to this place? The erosion happening here is primarily due to landslides, solar insolation on the exposed scarp, causing sublimation, and of course, wind blowing away material away from the cap. The polar region is also of interest if someone thinks of cryobrines or activity of liquid water. We have great examples from Phoenix Lander that saw development or growth of droplets over few sols on Mars. And you can see the size of the droplets grew, and that's because of salt-rich water that absorbed moisture from the atmosphere and just grew in size. The image in the bottom left, in the inset, you can compare the one on the left to the right. The white patch disappears on Sol 24 when you compare that with Sol 20, and that we think is volatile ice on the surface, which is unstable. Marian Mass's work from 2012 also confirms detection of gypsum, which is likely to be glacial in origin. And that also lets us think that there is some aqueous activity happening in the polar region as well. The spectra here just shows absorption bands, hydration absorption band at 1.94 and 2.21 and 2.24, which are indicative of presence of sulfates. So as we know, Mars today is dry, cold, and any liquid water is very rare and likely to be highly salty. So this plot here is a nice representation of surface temperature of Mars throughout the year. The blue line shows the mean annual temperature for the year. The orange solid line is average daily temperature, and you can see how it varies from the season on the x-axis, from spring, summer, fall, and to winter. So and the dotted orange line shows you the maximum and the minimum diurnal temperature for each of these seasons. And the salts on the plot show the range where it stays active. So this clearly shows the temperatures on Mars today will allow or does allow these salts to stay in brines and stay active as thin films on around mineral grains. So that leads me to ask a question as I'm exploring the polar deposits. What is the alteration history of the region here? Do we see any other signatures of alteration in the polar region? Basically, I have three major objectives in this exploration of polar region. That is to determine the primary composition of sediments, investigate aqueous alteration history, and then I'm also utilizing color analysis technique to understand sediment provenance of these sediments through an analog here on Earth. So this is a finest funded project and also a P-STAR grant that was funded to my advisor on the committee. Okay, so let's dive into the first section. We're looking at the North Polar region of Mars. On the left is a picture taken by Viking spacecraft. The white portion is the residual ice cap. The grooves that you see on it is the spiral trough that's caused by blowing wind, like cold polar winds away from the poles. And the darker regions are the dunes. To the right is the molar elevation map, and where the red and the white is the region of highest elevation. And you can see it's 3 to 4 kilometers higher than the lowest surrounding region to the polar cap. The polar deposit itself is over 2 kilometers thick, which is twice the thickness of Antarctic ice, and it's half the diameter of Antarctica. So it's a massive 1,000 kilometers wide deposits in the north, and which is hypothesized to have originated in last 5 million years. So previously, materials surrounding the polar ice cap was studied by my advisor, Professor Horgan, and she found lots of high calcium pyroxene and leach glass in the surrounding dune dominated region. And the spectra on the left are examples of what high calcium pyroxene detection would look like, which is on the top, and the leach glass at the bottom, where all of your iron is leached out, so you don't get those absorption bands at 1 and 2 microns. So again, reflecting maybe some kind of an aqueous activity. Okay, so for my study, I utilize CRISM hyperspectral images. The image on the left is a albedo map derived from MOC, Mars Orbital Camera, and the numbers in green shows the sites that were investigated and showed results in the study. The image in the center is an example of what an approximate true color image would look like at one of the scarps. And to the right is what happens to this image when we apply CRISM spectral parameters, which measures the difference in the spectral shape in the region, like throughout the image, and then you can map that diversity on the image itself. So here we can see like 2 distinct units appear to have difference in mineralogy, and the region in red shows that it's highly dusty, it's dominated by ferric dust, whereas the cavity region at the bottom is more iron, glass, and pyroxene dominated. So you can identify your regions, like variability in the regions, and pick up your regions of interest as you're studying the region. So here is what a lot of my time went into while conducting this research. So if you look at an average spectra from this site, the one in cyan and magenta color, you will see a strong absorption band at 1.5 micron and 2 micron, which is 1500 and 2000 nanometers here. And that shows strong presence of water ice. But that is not helpful to answer my question. So in order to do that, what we do is find out an average neutral spectrum, which here for these two examples is shown right under the two spectra of interest to us. And so find a dusty average spectrum that has similar ice band depth as at our region of interest. So once you have such a reference or a neutral spectrum figured out, you divide the two spectrum together. And what dividing does is it takes away the effects of dust and water ice and leaves behind a spectral signature that is representative of other materials that's present in the icy layers. So that's the result. The result is shown in step 2 after dividing, or what we called as chrism ratio spectra. And that clearly shows absorption bands at 1 and 2 microns and shows presence of mafic materials. And we are glad to have this result there. And because ratioing is a very subjective step, so you can have your spectra sloped upward or downward. So you apply a continuum removal technique to get exact band centers for these absorption bands, and that helps you differentiate mineralogy of spectra. For example, glass and high calcium pyroxene, the difference is there's a shift to the band center shifts to higher wavelengths for glass in this case. Okay, so here is the result. The region, the image on the left shows you is a RGB composite where red is more dusty, and our primary area of interest is this dusty deposit, and we're looking for what other materials are present in this these layers, which is primarily understood to have only dust. So the plot on the right shows diverse spectral signatures that we could find in these icy layers. The spectra on top, which is in red, it's completely flat. That is how a dust would appear spectrally on Mars, with no unique absorption bands. And then you have high calcium pyroxene, olivine, iron-bearing glass, and some tektites, and the last at the bottom is again leach glass surface. So a very diverse suite of mafic materials, minerals were detected in these dusty layers, which also indicates that it could have diverse sources, like because we're also asking how these things got into the icy layers. So this is one of the best findings that showed us about this surface activity that's going on the polar cap. So we are looking at a trough on the polar cap, and the slope of the trough, that is in magenta, is the equatorward facing slope. So we have winds blowing from north, and it erodes that equatorward facing slope and just blows away the fine-grained dust and leaves behind the coarser deposits at the bottom. And so we can, that clearly shows an evidence of how these different materials are entrained in the ice and differences in their grain sizes. And so it shows that all of these mafic minerals are much more coarser rather than fine dust. So what are the sources for these materials on the poles? So we are looking at a wind map of the polar cap, and this is a wind map of the current orbital configuration or the tilt of Mars, and it shows which has been so for last 5 million years. So the wind is almost driving everything away from the cap. So as we observed in the image of this region before, that the polar cap is surrounded by dune fields. So it is unlikely that wind would have blown sand from the surrounding dune fields onto the cap, because the wind directions don't say that. So there must be other ways how material got onto the cap other than the adjacent sources from the dunes. The detection of olivine was of special interest in the cap region, because the closest detection is at least 1,000 kilometers away towards the equator from the pole. And so something must have brought material from really far away from the planet onto the cap. So here are the two ways. One of the ways that we think material can reach the cap is the volcanism, where very fine-grained volcanic ash can be atmospherically buoyant and transported to the North Polar region. The study by Kerber et al. 2012 shows a cumulative accumulation by all known volcanoes on Mars could be 6 meters in thick, and that's not much at all. That's a very tiny fraction, especially because this is a cumulative of all volcanoes, and we know that the northern polar deposits is likely to be 5 million year old. So it's, if there ever was eruption in last 5 or so million years, and we could expect a very thin layer of ash in the ice from that source. There have been some crater-based age dating studies that volcanism might have been active in last 2 to 10 million years. These are studies conducted by Newcomb, Hauber, and Garvin, respectively. But what we think is a major source of sediments at the poles is that it's coming from impacts, which can ballistically emplace proximal and global lithics. And so the proximal impacts would emplace local country rock along with some melt like suivites. And as we go further away, the impacts that go further away from the poles, we would see more tektites sourced from them, and any distal impact that is greater than 15 kilometers in diameter anywhere on Mars has the capacity to emplace 40 spherules per square centimeter all around the planet. So this was from a study by Lawrence in 2000. So a lot of these coarse mafic material, which is coarser than dust, could be these microtektites or spherules sourced from all across the planet in the ice. So here we conclude that we have the polar layers of Mars contain mafic sediments other than just dust, and they are sourced from impacts and volcanic eruption. And that means these are radiometrically datable and suitable for quantitative geochronology. It also tells us that the NPLD records impact flux rates, eruption rates, and the results can help improve the radar models, which currently only considers all lithics as dust in these icy layers. And once you have these lithics on the pole, that can have an influence on the accumulation rate or of the PLD, which can influence the timing itself on how old we think these deposits are. So in my second chapter, I explored the southern polar deposit, asking similar questions. So here we are looking at the South Polar region. It's again on an albedo map. The region in white is the residual ice cap. So I'm looking at regions outside the residual, just outside the residual ice cap, which is mostly South Polar deposits, and that's light tone deposit on the albedo map. On the right is the molar elevation, which you see. And this is estimated to be nearly the size of Alaska, and it's about 3.5 kilometers in thickness, including the residual cap on top. Gravity models estimate the deposits to contain 15% dust, and we will see if there is anything else other than just dust. So what makes South Polar deposits significant is the South Polar is slightly older than the North. and it's estimated to be 30 to 100 million years. So it gives you a window to look deeper into the late Amazonian climate if you were to analyze the climate records of the southern polar region. So that's the importance that this site carries. So the region in blue is the South Polar deposit here, and all of the arrows indicate the sites of investigation in this study. So here's a result, sample of the result, I should say. We found olivines, high calcium pyroxenes, and glass again in these layered deposits. So, which again shows that we likely have a variety of sources for these material on the southern cap as well. Extending similar arguments to the South Pole, we look at the volcanic region around the South Pole. There is a giant volcanic province called Malia Volcanics. And all the yellow dots that you see are various other volcanic features that have been identified but not studied in detail. So we are not sure when the last spurts of eruption ever took place at these places. But if that was ever in the period in the last 100 million years, it is very likely that the lots of ash would have been emplaced on the South Polar cap through those eruptions. Similar arguments can be extended for impacts bringing material from all over the planet to the layered deposits in the form of spheroids, tektites, and spherules. So which also shows that just like the North Polar deposit, the South Polar deposits are also suitable for quantitative age dating. We could use these minerals since they have an origin from volcanism and impacts. So this is just a finding of the cap. We observed a detection of low calcium pyroxene signature, and which we thought might be of significance for someone who is looking at the volcanic development in the South Polar region of Mars, which we know is not very well constrained. So a second part of my second chapter was to look at alteration minerals within the polar layer deposits. And previously, we know very well that around the North Polar cap, which is on the image you can see to the right, sulfates are widely detected in this region. And even in the grooves that you see, which are the polar troughs, you have these signatures present. So this suggests an oxidizing, evaporative, and sometimes acidic conditions in the cryosphere, in the Martian northern cryosphere. However, sulfates are also known to have to originate from atmospheric photochemistry and just precipitating out of the atmosphere as well. So there are multiple sources, and the source is debated, and like which one is a major contributor here. And so we'll see where I get with my results. Another important reason to look for alteration signature at the pole is as this bright radar reflection that's observed within the South Polar layer deposits, and it's understood to be clay-rich deposits. But it has been alternately hypothesized to be subsurface lakes, which means the radar reflection is either from the clay-rich deposit or from subsurface lake as well. So that's why I would be looking for evidences of clay-rich signatures within the polar layer deposit itself. Here is an finding from my study. Shows sulfates are all over the South Polar layer deposits as well, just like the North. And so it's a most dominant alteration mineral. The spectra to the right showing an absorption at 1.9 micron and a shoulder or drop at 2.4 micron, and which is coming from sulfur oxygen bonding, and so it's likely a polyhydrated sulfate. So this signature was almost in all of the prism cubes that I investigated on the cap, and which was not that smeared by ice. So we could find sulfate signatures very easily. And we observed that these sulfates dominate the light toned layers, whereas the sediments that pile up at the bottom of the cap lack that signature, and which we think is because as these sulfate grains erode off the polar cap, because they are friable, they just grind away as dust and do not really concentrate as much into the sediment pile at the bottom. That's one hypothesis that we have for finding. Here are other alteration products that we observed. Top one, we have hematite. The second one, which we think could be zeolites, based on a paper from Pule et al. Studying the Phoenix landing site in the north. We did observe acid-leached sediment, and then some smectite-like signature could be varying from aluminum smectite to iron magnesium smectite. And all of these different signatures in the layered deposits indicate a very diverse kind of environment, from extending from something that is highly oxidizing and acidic to more alkaline and having varying water to rock ratios. So can South Polar regions support these diverse climate? Maybe in a different obliquity configuration of Mars. But an alternate explanation could be that these alteration products are likely garnered by impacts in the surrounding Noachian terrain, which we know contain more altered surfaces. Here we just compare how the north and south poles are quite different in their elevation. North one is in the northern lowlands, much below the Martian aeroid. And the south polar deposits are up to 5 kilometers above the Martian polar aeroid. The ages of these deposits are different, ranging from 5 to 100 million years. The accumulation factors in each of the orbital configuration would be different, and what I've mentioned here is for the current configuration. Sediment volumes are different. We observed that the northern polar region is surrounded by giant dune field, whereas the southern region appears to be clear of a lot of these sediments. Despite all of that differences, we observe, like within the polar layered deposits, the same type of mafic minerals both at the north and the south, and sulfates appear to be the most dominated altered mineral in the ice cap, or maybe in surrounding areas of the residual ice cap, which is the rest of the polar deposits. So that makes us think that the climate has been more or less very similar in the last 100 million years on Mars. So our exception to that would just be detection of smectites on the south polar region, but that we think is likely impact garden in the surrounding, coming from the surrounding Noachian surfaces. So we know both PLD contain amorphous and crystalline mafic sediments. Sulfates are the most widespread ones, and smectites are at the SPLD is impact gardened. So we can also, just like the North, core a South Polar ice core and age date them for climate records. And we also understand that the materials are sourced globally from all across the planet because of impacts. And the alteration environment is likely similar in last 100 million years at both the region. So in the third chapter, I investigated the role of color. And why is color so significant? Because it is the most, color images are the most abundant planetary data set, and color is an indication of compositional variation in the planetary materials that you're looking at. Here's an example of what a color analysis would do to an image. On the left is an enhanced true color image, and the right shows the result of color analysis done on it. So the primary goal of this chapter of my study is to use this technique to conduct sediment provenance, that is to reconstruct the origin, transport, and deposition of sediments um, at our analog field site. And so can color be useful to understand a physical and chemical variability in this and constrain the sediment history here? So this is the rover that we had at the field site. It's developed by Mission Control Space Services, a Canadian company. And on the right shows a tent where we had ground scientists inside who were in simulation. So they just had to respond based on inputs coming back from the rover, and few field scientists who acted as arms of the rover collecting data and bringing it back to and sending it back to the ground team. And so they were not allowed to have or tour the site of investigation, just have to respond based on inputs given to them. The project is called SANDY, which is Semi-Autonomous Navigation for Detrital Environments, which is a NASA-supported P-STAR project. This is our field site. We have glacier up north and a valley incised through the volcanic terrains, which opens up into the outwash plains, and characterized by braided river channels. You have wind deflated terrains, lots of sand drifts and dunes later on in the outwash, and have a large shield volcano as well. And so we had 3 sites of investigation: the yellow, green, and cyan dots, where the proximal, medial, and distal sites where we conducted our rover-based study. So here we're looking at a natural color image on the left, and on the right, we have changed the contrast of that image, which brings more color information, but still the albedo effects of the illumination is not eliminated. So when we apply a color analysis to it, the albedo effects are suppressed. Here is what we do technically. Like the plot on the left is, for example, red versus green. You can see how all the pixels are aligned, and it does not utilize the entire color space. So we apply principal component analysis, which is step 2, select a new axis for our data, and where the primary axis P1 is albedo, and the secondary axis represents color variations. So in this new transform space, the pixel values are stretched to occupy the entire space and rotated back in the final step into the original color space. So if you compare the first plot with the fourth plot, you can see the same pixel now occupies the entire color range that is available, and therefore the color of the image gets enhanced. Here is a result of doing that. And so we are something looking so homogeneous and uniform carries such color variation. We can see those color variations when we apply this technique. So what does those color mean? So we collected sample source rocks from the site and took their images and also their spectra, visible near-infrared spectra, and compared the colors with the spectra. So we see that colors like blue and green are coming from minerals, mafic minerals like pyroxene and olivine, whereas red, magenta, and yellow represent different altered minerals on the in the source rock or the sediments. The plot on the right shows how the visible portion of the spectra will look like for red, green, and blue rocks. And the red rock shows a strong absorption at the lower wavelength because of presence of ferric iron. We also looked how colors vary in the sediment that we collected. And so we sieved them into various bin sizes, ranging from less than 63 microns to greater than 2000 microns. And we see that the finer fraction appear more red and yellow, and their spectra shows presence of hydration and hydroxylation bands, which shows that more altered fraction goes into the finer material, and the coarser material is still much more mafic. So yeah, and in the interest of time that we have, I will move ahead and give you an important result from that we found was if you look at the valley itself, it appears to be dominated by blue color, and that's just because the surface of the valley is dominated by coarser resistant cobbles, which are much more mafic. And that does not mean the finer altered fraction is completely absent. It's just that the wind and the water just has driven out the finer fraction from the surface, but they are all present just underneath the top surface. So the colors are just indicating on what's on the surface, and much more diverse material can actually be present, which we have to be cautious about when just using the colors and understanding what materials are present on the surface. That was one of the findings here. Here is how we see color variations. We have red-blue ratio on y-axis and intensity of green on the x-axis. And we see that the source rocks are much more diverse in color range, whereas the sediment in the outwash plain, because of sediment mixing, has a much narrower range of color that we see. We also looked at how peak reflectance of the sediments that we collect varied across different grain sizes, and the finer fractions peaked at higher wavelengths compared to the coarser fractions. And that was standard across all our three sites, which were the proximal, medial, and distal sites. Although the distal site was much more red, which we kind of expect to have more weathered materials than the proximal site, and that appeared to be true from our plot. Here is an example of there's a lot going on in this plot, so I will just give you a brief idea of what we're doing. So we are in a way fingerprinting the source rocks using XRF element abundance data, and we have zirconium and aluminum plot here, and different source rocks have their distinct composition, and then tracing where the composition of sediments fall in comparison to the source rock itself. So we found there were two distinct grouping at the proximal and the distal sites. You can see where the yellow dots concentrate and where the blue dot concentrate. They are representing proximal and distal regions, and it's showing that there is some other source that's adding material to the outwash plane. And apart from that, this is an application of color at the field site itself. You can see a perspective view of the rover, and you can compare the colors of surrounding sediments to distant outcrops and try to correlate their sources, and also use that color for orbital images or, for example, images captured by drones. And that is very useful in extending local color information to adjacent regions as well. This is a good example of how color analysis would be used to pick diversity within the rover's workspace. And color analysis is a quick tool that helps us do that, achieve that. That finishes all of my third chapter as well. And we find that color analysis, along with VNIR spectroscopy and XRF analysis, can help us classify primary mineralogy versus alteration mineralogy, aid us in identifying diversity in targeting and sampling, and relate detrital samples with their parent bedrocks. So all of that can be achieved. Okay, I will end my talk here and open for questions for everyone.